morning, students. This is the topic, the alternating generator or AC generator. Now here at first I am showing you some armature being rotated in between two pole pieces. Now let us see what happens when the frequency of rotation, yani ki the angular velocity has been increased. So when the velocity increases, what happens? You can see in the oscilloscope that in the oscilloscope you can see the frequency has increased and the time period has decreased, and you can see in the galvanometer the positive and negative sweep has done more rapidly. It is about 10 and 10. Now let's to the direction concept. The direction concept you can understand by Fleming's right hand rule. The first finger you will be having the direction of magnetic field. The second finger or the middle finger is the direction of current when the thumb is pointing towards the direction of force or the motion of the conductor. We'll be looking at this one. You can check. This is an AC generator. Now AC generator, what happens inside? You might have seen it inside in your house or many places you have seen. So the North Pole and South Pole, there are some laminated coil that has been rotated, and that is known as an armature. Prior to that, let me also remind you about electromagnetic induction in a coil of copper. When you introduce the magnet, the current is going that side and taking out the current in the other side. Left and right sweep, it is taking place. Now let me talk about the part of the AC generator. This copper coil is called the armature, which is placed over an iron core, a laminated iron core. The shaft rotates the coil, the armature, and ABCD we have named it in between two pole pieces, north and south pole. The pole pieces are semi-cylindrical. Two slip rings are there to collect the induced charges, and they are connected to carbon brushes. These carbon brushes actually collect the charges and supplies it to the load. Here the load is replaced by a galvanometer. Now how this AC generator works? Inside the field magnet, when it is rotating, there is a change in flux. You know, E is equal to minus of d phi by dt, and phi is equal to NVA. N is the number of turns. You can see the direction of current is changing alternately. In the galvanometer you can see this one. Now when it is rotated, actually what happens? NBA cos of theta, theta is equal to omega t. Now this omega t changes, and because of that phi changes, and from Faraday's law is equal to minus of d phi by dt. Now let us see that in the armature, say it is making 0 degree angle, or the plane is making 90 degree. Now it has been rotated by 180 degree. Just see what happens there. Now earlier CD was lower and AB was above. Now AB is lower and CD is above. By Fleming's right hand rule, you can see the current is going into the CD and coming out of AB. So that is collected like this. Now CD will go down in the next half cycle. CD will go down and AB will go up. So because of that, what will happen? The current will come out of CD and go into AB. So this this is the current is in the opposite direction. I can see that once it is going from B1 to B2, and the other time it is going from B2 to B1 as it goes on rotating. Now let us see the graphical representation of the induced EMF. Now when you are rotating it, you can see the alternating voltage has been generated, and the oscilloscope output you have already seen in the first stage. So at t equal to 0 second, we have found no current because the flux is equal to maximum. Flux phi is maximum, and there is no change in the flux. Now it has been rotated, so let us rotate it. Okay, as it rotates, the EMF gradually increases. At t by 4 it will become maximum. T by 4, okay, 1/4 the rotation. Then it will be again decreasing. You can see the galvanometer also. It will now reduce when it rotates like this, and once it reaches t by 2, means half cycle is completed, it is rotated by 180 degree. At that time the voltage once again becomes 0. Now the current will reverse. At 3t by 4 it will become minus E0. E0 is known as the maximum EMF, and once again when it is rotated to complete the complete cycle, it will once again become 0. This shape of a graph has got a name. This is called a sine curve. So induced EMF is called a sine curve. Here this white line you can see, this is sine curve. So AC, what you have learned here, the AC generator, electrical generator converts mechanical energy into electrical energy in the form of alternating EMF and alternating current. Now see, once again we see the diagram there with the numerical part of it. You can check here. These were the two slip rings. The load, it is rotated in the anti-clockwise direction, and once QP is in the south pole, inside the south pole, and PS in the RS is in the north pole. North pole here is shown as green one. But the next half cycle, it has become like this. In the RS has gone inside the south pole, and QP has gone into the north pole. Now you can see the direction of current is opposite there. So AC generator, this is the basic principle of AC generator, and the field magnet, what's the construction you have already understood. This is for your noting purpose. You can pause and take the note. Now let me show you what exactly happens in the mathematical ways, the analytical treatment of this. Here n cap is the area vector, and phi is equal to nba cos theta. Theta is equal to omega t. So theta is equal to omega t. This omega t, later on you'll understand, it is also called the phase. So phi is equal to nba cos omega t. You can check the shape of the graph. Just now you have seen the shape of the graph also. So it is E0 versus E versus t at pi by 2 or t by 4. You see, pi by 2 is the phase and t by 4 is the time in terms of time period. Time period is capital T. The shape of the graph is like this. Now alternating EMF is that EMF which continuously changes in magnitude and periodically reverses in direction. Alternating current is that current which continuously changes in magnitude and periodically reverses its direction. Why it reverses the direction? Tell me. Let's see, this is the sine graph, so it can be easily understood from here. So E naught is maximum at t by 4 or pi by 2 phase, and the green one is the current one. At t by 4 it is, the current is actually passing through the resistance or the load. Its expression is I is equal to I naught sine of omega t. Both of them are at same phase because both of them has the phase omega t, and you can also understand that their minus I naught and E naught is also occurring at the same time, and at zero position also they are occurring at same time. You can check, there is another expression, that is E is equal to E naught cos of omega t. Actually it depends on the position from where the coil has started rotating, the armature has started rotating. So at t equal to 0, here the voltage is maximum and the current is also maximum. If it has not started from the perpendicular position but in the same plane as B, then the shape of the graph would be like this. At t equal to 0, the maximum EMF will be generated, and so the maximum current will also flow. These are different symbols. E and I are instantaneous value of EMF and current. E naught and I naught are called peak or maximum value of amplitude and amplitude of EMF and current. Omega is called the angular frequency, T is the instantaneous time, and omega t is the phase. Average or mean value. Actually, averaging in AC requires two types of techniques. The first technique is known as with the help of charge. You can see an AC has got two half cycles. One is positive half cycle, another is negative half cycle. The area of the I versus T graph or I versus omega t graph will give you the total charge. Now, because the current is changing at every instant, so we take a small interval dt, and dq will be equal to I into dt. Putting the value of I is the instantaneous value, I naught sine of omega t dt. In fact, the average or mean value of alternating current over half cycle, it is taken over half cycle. I'm telling you why it is that steady current which will send the same amount of charge in a circuit in the same time of half cycle as seen by the alternating current in the same circuit in the same time. Now, why half cycle? You see, Q positive in the positive half cycle would be equal to Q negative in the negative half cycle, and if you take the average over the whole cycle, it will be always equal to 0. So that's why you have taken it over half cycle. 0 to t by 2 or t by 2 to t. You can see if you integrate, Q positive will be coming 0 to t by 2 I naught sine of omega t dt. Little calculation will give I naught is equal to t by pi. So the mean value is what? Q by the total time. The time is t by 2. So it is coming out to be twice I naught by pi, or in other words, you can say 63.7% of I naught. So the mean value, mean or average value of the alternating EMF is 63.7% of E naught. It is on the basis of the amount of charge in the half cycle. Now let us take the root mean square or virtual effective value or DC value of an AC. Actually, it is on the basis of the heat generated in a circuit. See, the heat generated in a resistance R in our time t is H when the AC is I. If this AC is replaced by a DC voltage EV, then the current is IV. Then R, in the R, over the same time, if the same heat is generated, remember it should be, the time should be greater than T by 2. Why greater than T by 2? I'll tell you. So in that case, if the heat is same, then EV is called the RMS voltage of the AC and IV is called RMS current of the AC. So root mean square or RMS value of an alternating current is that steady current which would produce the same heat in a given resistance in a given time as is produced by the given alternating current in the same resistance in the same time. By Joule's heating, H is equal to I square RT. So it will be I square into dt. Putting in the values there, I naught sine omega t. So I naught square sine square omega t into R into dt. If you integrate it over the full cycle, say any time, it may be n number of full cycle, I don't mind, but for simplicity we have taken it 0 to capital T over the full cycle. So it will be I naught square R sine square omega t dt. Then by integrating sine square omega t, actually those who have mathematics as one of the subject, you can understand twice sine square omega t is equal to cos twice omega t. Actually it will be 1 minus cos twice omega t, and when you solve it, integration of cos twice omega t would be equal to 0. So it will be I naught square R t by 2. Now we have replaced omega as 2 pi by t here. So the actual value would be coming out to be IV is equal to I RMS is equal to I effective I naught by root 2. 1 by root 2 is equal to 0.7071. So it is 70.71% of I naught. Remember, the average when taken over half cycle for the charge, on the basis of the charge, it was 63.7%. But the same thing when we have taken it over full cycle or any time, it is 70.7% on the basis of the heat. Actually it is more convenient to find out this, because when the current changes the direction, then also the heat produced has got no change, because the current is squared, so the negative one will be converted into positive value. So because of that, it gives us a more authentic value. And remember, most of the alternating current apparatus, they use this technique by measuring the heat produced by a current, and that's why all the AC measuring instruments are called hot wire instrument. So root mean square value alternative can be calculated over any period of the cycle, since it is based on the heat energy produced. Do not use the above formula if the time interval under the consideration is less than 1/2 of the period. Now relative values, this is an important point again. EV and EM, you can see EV is the virtual value or RMS value, and EM is the mean value or average value. Mean is little less. Why it is less? Actually the reason is, when the flux changes its direction, just sweeps out some left to right or right to left, the flux is changing, then there is also some induced EMF which is not taken care of during the mean value, but during the virtual value it is taken care of. So because of that, we get the mean value is little larger than the mean value. So RMS value would be little more than the virtual value, will be more than the mean value. Usually we say that 230 volt AC in this part of the country we use, or this part of the world we use the RMS value. We say the 220 volt or 230 volt AC. There are some places in the world where it is other than 230 volt or 220 volt. So yeah, we always mention the value as RMS value. AC ammeter and AC voltmeter read the RMS value of the alternating current and voltage respectively. They are called hot wire meters because the temperature measured is taken out. The scale DC meter is linearly graduated, whereas the scale of AC meter is not evenly graduated because H is proportional to I. This is known as a phasor diagram. Check it out. What happens there? Actually, phasor is a rotating vector. You can see at different instant when the voltage phasor is reaching some places, you can see the perpendicular dropped on the x-axis, that is called reference axis, and y-axis are also known as their instantaneous values. Now x is called the cosine function and y is called the sine function, but both of them the instantaneous values. Now at different positions the value of current will be different, and depending on the phase, you can see the phase is changing. Those phases are omega t, then maybe pi plus omega t or 2 pi plus omega t. That way it is going on changing, and for that you can see the graphical pattern shown below. Now you see, I can see this rotates through one complete circle. Vx equal to v greater than 0 and vy equal to 0 at theta is equal to 0 degree. Now theta is in the first quadrant. In the first quadrant, theta is equal to 45 degrees, say, so Vx is equal to V cos 45 degree greater than 0, Vy is equal to V sin 45 degree, that is also more than 0. Now when theta is equal to 90 degree, what happens? Vx equal to 0, Vy is equal to V is greater than 0, like this. At third quadrant, it is theta is between 90 degree and 180 degree, so it is taken as 135 degree because these angles are at the interval of pi by 4 or 45 degree. So this way, when it is theta is equal to 180 degree, Vx is equal to minus V because in the negative quadrant, and Vy is equal to 0. Theta 180 degree plus 45 degrees 225 degrees, so Vx is equal to V cos 225 degree less than 0 because it is negative. So though it is a positive value, but it's Vx and Vy both are coming as negative, though V0 is positive. Now when theta is equal to 270 degree, Vx 0 but Vy is equal to minus V, and 270 plus 45 degree, that is 315, then we got Vx is positive but Vy is negative. You can check it out. So this is what is happening there. Putting the values, you can see. Okay. Right. So this is not coming anyway. So it is called R circuit. In the R circuit, you will be getting voltage I is equal to E naught by R sin of omega t. So voltage and current both are at same phase, exactly like in the AC generator. You have learned about it. And when you draw this phasor diagram, the shape of the phasor diagram would be like this. This is for E naught phasor and I naught phasor. Both are having the phase angle phi is equal to omega t, or phase angle theta is equal to omega t. Now this is R circuit. Now this is L circuit. E is equal to E naught sin of omega t. You can see whenever an AC is generated, AC is applied, a voltage VL is generated across the inductor L. Here we have taken a ideal inductor, so R is equal to 0. Then by the Faraday's law, VL would be equal to minus of L di dt. Again by KVL, VL plus E is equal to I into R, R is equal to 0. So E is equal to minus VL. So what do you get? E is equal to L di dt, because E is equal to minus VL, E is equal to L di dt. By solving it, you get di. Now when you get di, you can also find out I by integrating. Remember here you are using the indefinite integration. Now see, we have used it, I is equal to E naught by omega L minus cos omega t plus there would be a constant. But that constant we have taken as 0. The reason is the constant has the same dimension as that of current by dimensional analysis, and because it is not retaining any charge, neither it is producing any charge, so over half cycle, over positive half cycle, whatever is the charge, in the negative half cycle the charge is same, so the average value of the K will be always equal to 0. That's why the average current is not coming, so it is I is equal to I naught sine of omega t minus pi by 2, and plus K is taken as 0. Here we have taken chi L or XL equal to omega L, that is known as inductive reactance. It is the opposition offered by an inductor to an AC. Current lags behind the EMF by pi by 2 radian. So what you find here, the graph is somewhat like this. Here voltage would be leading the current by pi by 2 or T by 4. This phasor would be, phasor you can draw like this. This is voltage phasor, and it is lagging by minus I naught is lagging by minus pi by 2, so that is omega t, and this is omega t minus pi by 2. Remember, positive direction is the direction of positive direction would be the anti-clockwise direction. Right, the next one. Now it is for a capacitor. For a capacitor, E is equal to E naught sine of omega t, Q is equal to CE, I is equal to dq by dt. So that by differentiating the dt of sine omega t is equal to omega times cos of omega t. So it will be C E naught into omega into sine of omega t is becoming cos of omega t. But the form is actually, that is voltage by resistance or reactance. So we'll be putting omega c multiplied into 1 by omega c denominator. 1 by omega c is called xc, that is called the capacitive reactance. The capacitive reactance you can see, so the I is leading by pi by 2. So when at t equal to 0, when voltage is 0 but current is becoming I naught, the phasor diagram would be like this: E naught and plus 90 degree. So this is omega t and this is plus pi by 2, omega t plus pi by 2. Understood this? Variation of XL with frequency. If you draw this XL versus omega L, XL versus omega, that is, it is a linear equation. So L1 and L2, from there you can see L2 has got higher slope. Slope is the value of inductance, so L2 is greater than L1. And there is variation of XC with frequency. You see, XC is equal to 1 by omega c. So it is a rectangular hyperbola. How the shape would be, that is, so for two different capacity we have written C1 and C2 are the two capacities, and the X1 and X2 are the two reactances. Now see, Xc is inversely proportional to 1 by C, because X is inversely proportional to C, so C1 would be greater than C2. because x2 is greater than x1. There is another thing in DC circuits, omega is equal to 0. So if omega is equal to 0, xc is equal to infinity. So for DC, the capacitor offers infinite reactance and DC cannot pass through an capacitor. Inductance cannot decrease the direct current because direct current is not changing. So VL would be almost equal to 0. So it can only decrease alternating current. And capacitance C allows AC to flow through it but blocks DC. Now this is the most important topic, that is the RLC circuit or series RLC circuit. In the series RLC circuit, the applied voltage is E is equal to E naught sine of omega t. Then VL, VC and VR are the three voltages generated across L, C and R. They are in series. But remember, though they are in series, but VL equal to VL plus VC plus VR is not equal to E, because they are phases and their direction is not same. Remember, VR is equal to I into R, VL is equal to I into XL, and VC is equal to I into XC. In our specific case, we have taken XL is greater than XC. So in the R circuit, current voltage are in same phase. So in L circuit, current lags behind voltage by pi by 2, and number that is for VC. VC is lagging behind the, so here the voltage is lagging behind the current. So because we have taken XL is greater than XC, so VL is greater than VC. So VL minus VC is what? It is along the positive y-axis. So VL minus VC upon VR, if I draw by vector law of addition, we got E is equal to root over VR square plus VL minus VC whole thing square. This is when written as I into R whole thing square, then IXL, IXC. We got the I is equal to E by another constant. It is called impedance Z, and its value is R square root over R square plus XL minus XC whole thing square, irrespective of the fact that whether XL is greater than XC or XC is greater than XL. So Z is equal to root over R square plus XL minus XC whole thing square. XL and XC, the values we can put in, and tan phi is equal to X modulus of XL minus XC by R, or putting the value of this omega L minus 1 by omega C with the modulus, we can find divided by R is the phi is the phase difference. Tan phi is equal to XL minus XC by R, so tan phi is equal to omega L minus 1 by omega C. Some special cases are there. Let me show you the special cases, but prior to that, let me draw a graph between Z and omega. The graph will be a parabolic one. When at omega is equal to omega naught, omega is equal to omega naught, you will find that XL equal to XC, and because of that, the reactive part will become 0, the entire impedance will become resistive only. But in case a frequency we take omega 1 which is less than omega naught, here XL would be less than XC, and in that case the circuit will be having a current leading the voltage, and this is known as XL less than XC is called a capacity dominated RLC circuit. And here phi is negative, tan phi is negative or phi is negative, and here the current leads the voltage. There is another part where omega 2 is greater than omega naught. Omega naught is called the resonance frequency. So in that case XL is greater than XC. When XL is greater than XC, then tan phi is positive. Just look at the first expression. 10 phi is positive and phi is positive. So here the current lags behind the EMF by phase. Okay, whatever value it comes out to be with the 10 phi, that is the thing. So an LCR circuit is called inductance dominated RLC circuit. The most important one is XL is equal to XC at omega is equal to omega naught, and in that case the current and the EMF are in same phase, and the entire circuit acts as a resistive circuit, a purely resistive circuit, and here the current and voltages are in the same phase. Now I talk about resonance condition. In the resonance condition, the shape of the current versus omega graph is as shown, and at omega is equal to omega naught or omega r, we get the peak of the I naught. It's I naught max, but the I naught max actually depends on the value of r. Higher the value of r, the flatter is the curve, and we can see that the value of I naught max is decreasing. There is another part, that is I naught max divided by root 2, that is called half power current. Half power current, you can easily understand that at different frequencies the current is changing, so the power is changing. At some frequency the power is becoming I naught max square into r, that is the P maximum. So that value is known as half power current, and the frequencies corresponding to them are known as half power frequencies. The difference between this omega 1 and omega 2 is called the bandwidth. So we can write one quantity called delta omega is equal to omega resonance minus omega 1, or omega 2 minus omega resonance, that is known as the half the bandwidth. So total bandwidth is 2is delta omega. Quality factor or Q factor is defined as the ratio of resonant frequency to the bandwidth. So Q factor is equal to omega r by twice delta omega. Delta omega can be shown to be equal to r by L. R is the resistance and L is the inductor. Remember, this occurs only when this is an RLC circuit. In case XL equal to 0, it is called a CR circuit. In case XC is equal to 0, it is called LR circuit. But remember that they do not produce any resonance. So by solving, you can get Q is equal to VL by VR at resonance, or you can write Q is equal to 1 by R root over L over C. That is the expression for Q factor. LC oscillations, you can check it out. This is only to be done with a qualitative way. No quantitative analysis is there for you. Actually, my 40 minutes is almost up. You can see that is a current versus time graph, or the charge versus time graph here when the resistance is equal to 0. Remember, LC circuit is a tank circuit, is also called tank circuit. Is a theoretical circuit where R is equal to 0, but actually R is never equal to 0. So the shape of the graph is not exactly like this. So in that case, it is called a damped oscillation. So the damped oscillation looks like this. This part, you can find out the value of omega r with the help of a second order differential equation. So the value is omega is equal to 1 by root over LC. That is also called the natural frequency of the LC circuit. I talk about transformer. This is a transformer, and here too there are a pair of coils that is wound over laminated iron core. The EP is the EMF induced in the primary coil, and ES is the EMF induced in the secondary coil. ES by EP is called NS by NP. Remember, only NS by NP is called K, or the transformation ratio. EP by ES is not transformation ratio, it is ES by EP, output by input voltage. For an ideal transformer, output power is equal to input power. So ES into IS equal to EP into IP. By solving, you got ES by EP is equal to IP by IS equal to K. K is known as the transformation ratio or the turn ratio. You can find out an expression for that. But there is another term called efficiency. Efficiency is the output power by input power. So for the output power equal to input power, we will be getting eta into IP by IS equal to ES by EP. So you can say IP by IS has got another expression for the efficiency not equal to 0, not equal to 100%, K by eta. But eta is in most of the cases equal to 100%. So eta is equal to ES by IS into ES into IS by EP by IP. So these are step up and step down transformer. There are some energy losses. In the step up transformer, what happens? NS is greater than NP, and in the step down transformer, NS is less than NP. Okay, some losses of current. Actually, this is a question. Leave this question right now. It will be in my live class. You'll be understanding it. How to do this type.